Well, very exciting. I'm very happy to be here with everybody. So, before we begin, I don't have any friends. You are all my friends now, and I need proof to put on my MySpace. So, we're all gonna do a selfie, and we're gonna all yell BCI. I need to update my MySpace profile. So, everybody, 3, 2, 1, BCI! Come on, BCI! 3, 1, 2, 3, BCI! Yeah, that's what I'm talking about. All right, so I think I can begin by talking a little bit about myself. As a kid, I wanted to understand the what, the how, and the why of the world. I was a very existential high schooler. I would walk around, kicking pebbles on the ground, thinking, who am I? What am I? No, actually, it wasn't that bad, but I was, we think about these things. And I thought that the answer to these questions was going to come from physics. I needed to understand the constellations of the universe, what is going on out there to understand what's going on in here. But then I thought to myself, well, the discoveries that we've made as humans didn't really, it's like the physics, the biology, all these things, they came from somewhere, the brain. And so then I started getting obsessed, and I really wanted to understand what makes us tick, what allowed these discoveries to happen, what made us alive. And so before we begin, I think it might be kind of cool to see a sort of portal into a future that I imagined a few years ago. Some of the things that we'll see here have happened already, and some have not exactly. And we'll get into some details as to what happened and why was it possible. And I'll have a quiz at the end. And the question was going to be, can you find the BCI device in the video? There's many hints, so hopefully you can find it. All right, where was the BCI device? The watch, yes, a smartwatch with EMG. While the current EMG system that Meta came out with recently isn't a smartwatch, we can imagine that in maybe a year or so, we're gonna have smartwatches with these EMG devices. So that prediction became true. And there's other sort of predictions there that we can talk about in the future. So, I know it's a little taboo, but I think it's important to acknowledge the animal subjects that take a lot of the heavy role in a lot of the discoveries and medical advances that we take for granted. A lot of animals really contributed to so much deep understanding of what it means to be alive. And oftentimes we forget about that. So I just wanted to take a moment to remind ourselves that animals contribute a great deal to the advances of our lifetime. What is BCI? Brain-computer interface. It was coined in 1973 by Jacques Vidal. He has a really good definition. I like it. Utilizing brain signals in a man-computer dialogue as a means of control over external processes such as computers or prosthetic device. I think it's a good definition, but the way that I think about it is a little bit more general. I see it as a system that utilizes intentional or unintentional neural signals from the body or mind to control external processes. A few years ago, I started trying to track how many papers there are that accumulate over this kind of research. So on the left, you can see the sort of keywords that I used, and I tracked from 1970 all the way to now the sort of progression of BCI research. And roughly, you can see that it sort of doubles every 5 years. But now from 2020 to 2025, the PowerPoint slide isn't large enough to capture the amount of papers. And I'm starting to see, or I believe, that we're going to start seeing a sort of exponential growth, much so thanks to AI, which is going to be very interesting. BCI, they're sensors. They try to detect signals. What are these signals? So before I start going into the details of the BCIs that we're going to talk about, I think it might be important to illustrate what a BCI is detecting. So we're going to go into a tiny, tiny, tiny little side quest on understanding how neurons work. Our brain is organized with about 100 billion neurons. And those neurons send signals down the spinal cord into the peripheral nerves. And these peripheral nerves then innervate muscles, and these muscles then allow action and movement to happen. How does this happen? Neurons take many different forms and shapes, but generally we can think about it like this. There's three components. We have the receiving end, an axon, which we can think of as a highway of information, and then the transmitter end. When a signal comes in and it's powerful enough, then the neuron sends an electrical pulse down from the receiving end to the transmitter end. And the way that happens is we have these sort of gaps, tiny little gaps between neurons. And when the neurons send a signal to another, they send neurotransmitters through these little gaps. These little transmitters attach to receptors that then allow channels on the surface of the cell to allow charged particles in. These particles are called ions, and some of you may recognize them as electrolytes. So when you're drinking Gatorade, Powerade, you're drinking these ions. Once they enter the neuron, we start seeing a sort of directional change of voltage. So as enough charge flows in from these channels opening, what happens is an action potential. That's what it's called. Now there's a huge rise. Channels are opening everywhere. Ions are flooding in. And then we start seeing a directional shift where the ions are flowing from the receiving end all the way to the transmitting end. And that's how signals are sent from one neuron to another. And BCI, these devices, what they're trying to detect are these changes in voltage. These tiny little changes of voltage are the language of the brain. And you can imagine that as we move farther away from where these neurons occur, then the signal becomes noisier. And so the device that's trying to read these signals is going to have a harder time and might have to use different methods to be able to pick up these signals. So there's basically two categories of BCI, invasive and non-invasive, and they sound exactly like what they mean. Invasive is a BCI that requires to cut you open. You need to go to surgery. There's going to be blood. A non-invasive BCI is just one that can rest on your skin. It's not going to be super uncomfortable. There are some that are a little uncomfortable, but generally they're not that uncomfortable. We can see from the surface up here, we have like EEG, FNIRS, and even fMRI, which doesn't have sensors that touch the skin. It still is able to be considered a form of BCI if it's used in a certain way. ECOG is now at the cortical surface, and then we have microelectrodes. Those are the more invasive ones, and some of the ones that are responsible for the earliest of BCIs. Over here on the left, we have what looks like an EEG cap. This is a wet EEG cap, meaning that there's little liquid gel that helps facilitate the conductance and allows us to detect those signals a little bit better with a cleaner signal. And then over here, we have one of these more invasive BCIs, one that's implanted. They had to do some surgery and open this person up. Here we are in a zoomed-in version of this. You can see those microelectrodes. Some of these have like little nails. They sort of penetrate the cortical surface. Yep, yeah, I see some people grimacing. It's kind of intense. And then over here, we have slightly less invasive, but still requires opening you up, the ECOG over there, electrocorticography, and that touches the surface of the brain. It doesn't necessarily need to poke it, but it can still cause a foreign body reaction on the cortical surface of the brain. And again, as I mentioned, you see, as we get closer to the source, there's a higher signal-to-noise ratio. But as we move farther away from the source, the signal becomes more noisy, and we start getting into problems. So in general, it is the case that invasive BCI or any of these sort of implanted electrodes will have a cleaner signal, and you can sometimes record even from a single neuron with high resolution. But how did we get here? How did we get to the point where we have metal things implanted into our brain or sensors at the surface detecting signals that can then be turned into motor movement? There's a really rich and long history of BCI that starts way back. Now, this timeline isn't comprehensive, but it sort of highlights some of the general landmark moments in the history of BCI. And so we're going to travel back to 1791, actually 5 years before 1791. So strap on your seatbelts, get some popcorn. Is there any popcorn? No, there's no popcorn. Okay. Oh, yeah, there is popcorn. Yeah, that's what I'm talking about. All right. Now, front row seats to 1786. So what's the difference between you, a living, breathing human, that can walk, talk, smile, laugh, versus a stone on the ground? This question sounds kind of silly, but it was a very important philosophical question that a lot of philosophers, intellectuals, scientists really wanted to understand. What is the difference between the living and the non-living? The leading theory, vitalism. That there was a vital force, a vital spirit that animated the living. Nobody knew what this vital spirit was, but it was there. Maybe it's like a soul. It was there and it animated the living. Enter Luigi Galvani. He was 19 years old. He was in the, actually he was not 19 years old. I'm thinking about another scientist that I'm going to talk about soon. He was actually an aging scientist. He was shy, but he taught anatomy. And he wasn't really interested in a lot of things, but he was a good physiologist. He would do a lot of experiments, open animals, study their physiology. And then one day, he was working on one of his experiments where he had severed a frog leg. And then an accidental spark all of a sudden made that leg twitch. He was confused for a second. Wait, what just happened? That frog leg just moved. Did anybody see that? It just moved. And he was confused. What happened? Why did that frog leg twitch? And he became obsessed. So for the next 5 years, he was just trying to understand, how did this little spark end up shocking this leg to make it twitch, make it move, make it wiggle? And then after those 5 years of working hard on this, in 1791, he published the first paper. And he called it Animal Electricity. And he told all his friends, hey, everybody, I think I found it. I think I found what is this vital force, this vital spirit. It's animal electricity. With his own money, he went ahead and started distributing his findings to a lot of leading researchers at the time. One of these went by the name of Alessandro Volta, which some of you may recognize. Volta, he was a strong character. He got these papers and immediately started being quite outspoken about how animal electricity was a fraud, didn't make sense, it was just BS. No, it's not animal electricity. What we're seeing here are metals. Metals are creating this charge, are creating this movement, and just the movement, the wiggling of that frog leg is just an artifact. This is known as the Galvani and Volta debate. They went back and forth. But Galvani, he was more shy, he was more modest. So in some of these responses, he published anonymously. He didn't like controversy too much. But Volta, he was obsessed. He kept going, stacking metals together, trying to find what proof, just ultimate proof that animal electricity, that's BS, it's all about the metals. And in one of these stacking experiments of all these metals, he invented the voltaic pile. And that, my friends, is the first battery. He was obsessed. And just from a spark, the electric age began. We're now in 1803, London. It's foggy, as it tends to be. And we have Giovanni Aldini. He is the nephew of Luigi Galvani. Like Galvani, he also had a little bit of obsession in him, and he believed in his uncle. He believed in animal electricity. He believed that there was something there. And he took his uncle's experiments to the next level. He moved away from frogs, moved to bigger animals, and eventually to a human cadaver. So in 1803, January, in London, foggy day, a man has just been executed, and he has been speedily not teleported, that would be amazing. He was speedily transported to Aldini. Aldini was in front of a stage, a packed theater. Everybody was waiting. What's going to happen? Morbid curiosity, but also a little bit of hope. Aldini then took, ironically, a voltaic pile, the one that Volta invented just a couple of years before as a result of the whole Luigi Galvani debate. So it's kind of ironic you're using the voltaic pile, but anyways. So he's using the voltaic pile to send electricity to different parts of the limb in this dead corpse. He goes to the face starts to contort, there's smiles, all of a sudden there's blinks, a lot of different things are happening. He then goes to the arms fling open, he then goes to the spine, and then all of a sudden the body rises. Could it be that now the impossible might be possible? That for the first time, we may be able to bring back the dead to life? We'll zoom in a few years later. 1815, we're in Indonesia, Mount Tambora. It's a volcano. It erupts. One of the largest eruptions in recorded history. In fact, the largest. So large that it's about 2 million Hiroshima bombs. This eruption plunged the world into darkness. 1816, the following year, became the year of no summer. In this year, there were a few writers, a couple of poets, Lord Byron, Percy Shelley, and Mary Shelley. They were taking a stroll, just hanging out, when the weather got really bad. After all, it is the year of no summer. Lightning begins to strike, thunder. It's a scary night. They huddle together, lit by candlelight. Lord Byron whispers to them, maybe we should have a challenge. Who can write the scariest ghost story? So for the next few days, they start writing, each have their own stories. And Mary Shelley writes one. In this night, this foggy night, lightning, rain, all from a volcano, after discussing with their colleagues about Aldini's experiments, about the technology of the time, Frankenstein is born. So we have from a spark in the leg of a frog, we have what led up to a debate that led to the voltaic pile, the first battery that sparked the electric age, modern physiology, and brain-computer interfaces, just from a frog leg, including modern, well, not modern, but one of the first science fiction stories. So it's kind of interesting to see how just a simple question, what makes life alive, led to all of these discoveries. What is the difference between the living and the non-living? So now we continue on our journey of our time machine. A lot of great progress was made in the following years. Notably, in 1893, a military exercise. There were a bunch of men, military, marching with artillery, cannons, horses, drawing all this heavy equipment. And a young man by the name of Hans Berger was thrown off of his horse. And soon, there was going to be a military cannon that was going to run him over with a horse. He was able to move quickly, switch, and then boom, survive. But at the same time, that exact same moment, a few miles away, his sister was taking a stroll with her father. And she had a feeling, a dark feeling, that something bad was going to happen to Hans. So she told her father, we must send a telegram to Hans, warn him that he's in grave danger. When Hans learned about this, he knew exactly what this was. It was telepathy. There was something connecting them. He stopped all his studies at the time. I forget exactly what he was studying, but he switched. His main mission for life now was to find the truth of telepathy. He ended up inventing EEG for humans. It had been done before with animals, but he was the first to do it with humans, and he was the first one to discover alpha waves. And then in this picture is one of his equipment that he used to detect the earliest EEG signals. 1963 was an interesting year, a very, very interesting year. So there were massive advances by Denise Alb-Fassard. She could be said to have been inventing the first microelectrode arrays, and later on was able to publish some of the first thoughts on stimulating and helping people with Parkinson's. Around the same time, over in Russia, Natalia Bektereva was also working on things like this and may be credited with being the first one to do deep brain stimulation, also potentially to help people with Parkinson's. Unfortunately, maybe due to sexism, also the fact that where she was in Russia was very remote, a lot of the work that she did was not recognized until much later. But in 1963, something also very interesting happened. A man by the name of Jose Delgado, also a physiologist, was able to stop a bull in its tracks. He implanted an electrode into a part of the brain of the bull that was remote controlled via radio. He had a remote control, had an implant on that bull, and what he was able to do is, I don't know if you see it in the video, but on his left hand, he's holding that remote. And in 1963, this could be the first wireless BCI control of an animal, which is kind of crazy. I even found a New York Times article where they talk about it. 1963, it's a long time ago. In the 1960s and 70s, a lot of really, really great research was done. But in the interest of time, I'll just talk about two more. So Edmund Duan was a physicist, and he was at Brandeis University. He also did a lot of other experiments, some of them covert for the Air Force. So we don't know everything that he did. A lot of it probably ended up being unpublished. But he was also very interested in EEG and being able to find ways to use brain signals to control devices. So in a little-known demonstration, he was able to turn a lamp on and off with EEG signals using alpha waves. And then later on, he was able to use the same method to perform Morse code. Obviously, it wouldn't be the most efficient way of doing Morse code, but he still did it. He had a friend at Brandeis University, a music professor that went by the name of Alvin Lucier. He was an avant-garde composer. And Alvin really liked Duan's research. In fact, so much so, and I bet they were friends too. I mean, they were both musicians. They probably jammed together. Liked the research so much that he borrowed the equipment from Duan and performed the very first, I believe, BCI music piece. He had EEG connected to his brain and had it control instruments that would then play music. And by the way, that man standing, putting that cap on Alvin Lucier is none other than John Cage, another famous avant-garde composer. You may know him from that song 433, which is just a song where for 4 minutes and 33 seconds, performers are on stage, but they do nothing. Over here, yeah, I know, it's avant-garde. So over here, could we get sound for this one? I said that there was only one video, but there might maybe. Okay, there we go. So I'm just gonna speed through this, but that's him. This is an 1988 rendition, not the original from 1965 that was recorded. And what you'll see here, I'm just gonna move forward. So what's going on here is the EEG cap is connected to some filters and some amplifiers. Those amplifiers are then connected to speakers. The amplified signal is actually just causing the speakers that are attached to these instruments. So I don't know if you can see, but for the drums, there's a speaker literally on the surface of the drum. So it's not like there's like a stick being maneuvered. It's just a speaker that causes vibrations, which then causes the snare to sound, the cymbal to sound. But in a really interesting rendition, like this is a beautiful example of how music and art can interact with this type of technology. Thanks. All right, let's zoom forward. So in 1998, might be argued to be the first human BCI by a man, Philip Kennedy. He was also a scientist that was quite obsessed with this. The first human BCI could only do on and off states, but then the second one was able to move a cursor on a screen, and these are screenshots from that period of time. Unfortunately, Philip Kennedy ran out of money. He wasn't getting grants anymore, and he still was passionate about BCI. He wanted to help people, bring back agency to people that lost it, and he had no money to do it. So instead, what he did, he went to Belize to undergo surgery to get an implant himself, so he would be the subject. He would study himself. Unfortunately, the surgery didn't work so well, and the sutures started opening. So he only was able to have that implant for about 80 days before he had to take it off. But nonetheless, his contributions also helped spark a lot of the modern BCI that we know that led to the 2000s. And I think another very important contributor to BCI is someone that people don't really know that well, and that's Miguel Nicolelis. So Miguel Nicolelis did a lot of stuff with monkeys. For example, in this video, you see the monkey is controlling a cursor on a screen using that joystick. Turns out the joystick is not connected at all using his mind. They train it by first using the joystick, finding a mapping between the joystick movements and the brain signals, then they disconnect the joystick. And this might look a little bit like something we'll see in a bit from a newer company. Nicolelis also did things where we had monkeys controlling robot arms, and what might be the first ever transcontinental, international, remote control of a robot. He had a monkey with a BCI at Duke University control a robot in Kyoto, Japan. That's kind of crazy. And this is all happening like 2003. All right, we're moving forward. So another really, really beautiful, this is one of my favorite videos of any BCI, and you'll see why. So this patient was paralyzed from the neck down, and what we're going to see here from 2012 is, there's no audio in this one, is going to be her controlling an arm with an invasive implanted BCI. She's trying to grab a bottle, and I'm just going to zoom forth a little bit. And there's something that happens at the end that reminds us as to why this kind of research is so important. Success. And then next up is putting it back. And then over here, her face. And that smile, that she succeeded. This is beautiful, and this is one of the 2010 sort of advances. But it doesn't stop there. In 2023, what might be considered the first brain-spine interface was made, and it's actually really, really cool. So the patient that they had a spinal injury. So basically, there was a disconnection between the signals from the brain and what would be transmitted to the peripheral nerves to allow for movement in the legs. So what they did is that they did two things. They had an invasive BCI on motor cortex of the brain at the top, and then they created a second device, a stimulator. And this stimulator would be placed around the spine. And they created a mapping to then send the intention of the motor signal so that then it would innervate the nerves that would lead to movement in the legs. And you can see here from this video, when the device is turned on, when like the digital bridge exists, he is able to walk. But then when it's turned off, and they turn it off for a while here, I think it stops over here, then he's able to start walking again. The sort of capabilities that this might provide are kind of crazy. What was once thought to be like kind of impossible. How do you bring back movement when like the nerves themselves are no longer there? This is not a robot. This is, you're using your own body to regain back agency. It's pretty cool, and the future seems very promising. But, you know, I've talked about all these research findings, and some of you might be wondering, well, when I think of BCI, I think of a couple of things. Things that I see in the news, things that I see in the media. Some of you might think, hey, what about Neuralink? Everybody knows Neuralink, right? Well, as you can tell, a lot of these experiments look very similar to the ones that happened 20 years ago from Miguel Nicolelis' lab and some other works from other people. And I will say that there's a lot of innovation that they have been able to do, not necessarily in like brain-computer interface per se, but they have a robot surgeon. And when you open the skull, the heart pumps blood, and that blood causes wiggling of the body, wiggling of the muscles, wiggling of the brain. So a surgeon that's trying to implant electrodes, thin ones, might hit a vein because the brain's wiggling and moving. So their robot surgeon was really capable of finding precision and not hitting veins as it's going and inserting these electrodes. And they've also done some interesting things, like a modern approach to BCI, where you might use a magnet to charge the device without having to use a cable or anything like that. Another company is Synchron. This is a minimally invasive device, so you don't need to open the skull. You open the jugular vein here, and they insert the device up through the vein, and it goes all the way to the brain, and what they call a stentrode. And you'll see in a second, as it moves to the next portion, that once they go in, they're able to release these electrodes, this little mesh that then spreads and is then able, here we go, spreads and then is able to detect the voltage changes of neurons nearby around motor cortex. So another one is precision. They also like to promote the idea that it's minimally invasive. In the previous one, it's a small insertion up through the veins. In this one, it's just a little slit. And then they just slide that in. And so you don't have to open up a lot. Regardless of how minimally invasive they are, they do require opening you up. And that has its consequences. So what is the future of these sort of invasive BCIs? Well, I've talked about a lot of these things. We saw how, in the case of Philip Kennedy, the surgery could go bad, and there could be, you'd have to remove it. There's another issue, too. The thing with these, metal sensors is that they're rigid, and the body doesn't like that. As soon as you implant something, the body starts to reject it. It starts sending a bunch of proteins and cells to say, hey, this is a foreign substance. So then you start acquiring noise in your signal. And you also move, there's life happens, the brain jiggles when the heart beats. And so these sensors are gonna not stay in the same location where they were implanted. So all the classifiers that you build to detect movement are not gonna work as well because now it's not covering the same population of neurons. There's a lot of issues that happen with rigid electrodes. So what's the future? Well, so a lot of people think it's gonna be flexible sensors, flexible electrodes. So in this example, there's a lot of images here, but what you can see here is a mesh that is able to bend and integrate with the surface. This is a mouse brain. And what they were able to do in this experiment is they were able to track the lifetime of a mouse. They were able to track single neurons by using this more flexible sensor. And there's many ways that people are trying to find these flexible sensors. Some of them include hydrogels, which you can think of just like gelatin with sensors inside. And they have found that sort of a more flexible, maybe with enzymes and coatings that allow it to increase the biocompatibility has helped. This is an active problem because you can imagine if you have a surgery to regain mobility, you have a company, and that company goes bankrupt, who's going to remove the sensor? What's going to happen? So if you have something that's more permanent, that is more long-term, then it's better for everybody. And also, unfortunately, if the company goes bankrupt, then you're still in trouble. And this has already happened, actually. So there are people that have had implants that had a company go bankrupt, funding ran out, and they had to deal with it somehow. Usually they have to go to a doctor and get surgery, but they weren't the ones trained for the implant, so it gets very complicated. And this is one of the dangers of invasive BCIs. But then again, this is not commercially available, and is there going to be a moment where we might want to volunteer for this? Well, we'll get into that. Another big company was BlackRock Neurotech. This company is very interesting. They were the ones responsible for a lot of the early BCI with the Utah array. And if you remember from a previous slide, it's one of those little squares that had tiny little needles that would hit the cortical surface. So they've gone through a lot of changes, a lot of money problems, a lot of reorganization. And interestingly enough, in 2024, a crypto company bought them. And I was like, what? That's okay. I guess someone needed to save them. And then in 2022, they released this video promoting, we've developed a new technology, the Neurolace. But then they went silent, completely silent. I was like, wait, all right, well, I guess that was just an announcement of something that never is going to come. But recently, there was a paper that was published where they were describing the flexibility of this sensor. And so it seems that they're still alive and doing active research. But the question then becomes, do we really, really, really need invasive BCI? Is it do we need to cut you open? Do we need to go deep into your neurons? Well, for people that need it, I think that that's still valuable because the resolution that you get from being able to detect neuron activity at a singular level is quite impactful and important. But for the everyday person, I don't think invasive BCI is really needed when we have non-invasive BCI. It is the case that is noisier, but there's a lot you can do. And as an example, some of you might recognize this. This is Control Labs. It was a company founded in 2015, and they weren't using new technology. They just found a better form factor for it, creating a wristband that would detect EMG signals, so basically muscle nerves that would innervate the fingers. And then they were able to help people that had lost some limbs because you just needed to put it on the list. So if you had lost your hand in an accident, you could wear this device and bring movement back. If it was an arm, if it was VR. And in 2019, Facebook bought them. And this year, we finally see the output of this creation. So over here you can see, I don't know if you guys follow a little bit of the Meta announcements, but the new Ray-Ban also came potentially with a paired EMG wristband. And now we have augmented reality, which you can control just using subtle movements of your hands. And the precision of this is really, really, really good. Again, non-invasive, it's on your wrist, not even on your head. But the innovations still keep coming. So I talked a lot about invasive BCIs and some of the cool things I have been able to do, like controlling robot arms. But categorically, in the research that I do, I technically do mind reading, but it's not mind reading in like the classical sense. I can make predictions about what you're thinking about, but it's not super, super precise. It can be, but it does take a lot of work. So in 2023, a lab in UT Austin was able to mix a bunch of different methods, including the use of GPT-1 to read people's thoughts. So they were imagining sentences. They were able to use a decoder to reconstruct those sentences. They were watching a video. They were able to reconstruct with words what they were watching. If they were silently saying it to themselves or reading it, they were able to decode that. The accuracy of this wasn't super great, but it was still pretty good. So take, for example, you can read those examples, but a better way to think about it is, okay, we have, someone eating a burger, and instead of the decoder saying, I'm eating a burger, it might say food burger, but it's still getting pretty good. Another thing is image reconstruction. So image reconstruction is a field in the space where if you see an image, in the research that I do, I can probably classify, okay, you might be thinking of an animal, but I can't reconstruct what you saw. And so this field of image reconstruction is about reconstructing what you see. So on the left-hand side, you see what was presented to the participant, and then what I'm about to show you is what was able to be reconstructed using stable diffusion and with work from Stability AI and a colleague of mine. They were able to reconstruct this with pretty decent accuracy. And this is, this is like now 2 years old. And they've now optimized this and made it much better. And there's more examples here. Reconstruction. So this brings us to a lot of questions about what is the future going to hold? What is privacy? What is agency? Now that we have our signals potentially read, what is the future going to look like? And I'm not trying to scare anybody here. I think like the future is going to be very, very bright. But I think also we have to start thinking about what our freedom and free will looks like, what it means to us, and whether, we have to start thinking about finding ways to allow this technology to happen, but happen under our terms. And I don't know if that's going to happen. And so, for example, in this video that I had showed you before, we have like a sort of setup of the future, where we have a phygital retail. The store is equipped kind of like a website where, it makes a connection with your smart glasses, knows that you're there, and starts placing stuff on the actual physical spaces to augment your reality. But there's many layers of protection there, where like if you do not want to be tracked, you can set it as a default and things like that. Where your wristband that has information is like all calculations are done locally on device versus being sent to a cloud where people can find out your medical condition and then maybe tell your insurance company that this person has a medical condition. You need to raise that up. This is not so much of a problem in Europe because Europe does a really great job of taking care of its people. But in other countries, it might be a little bit different. So because of this and like my worry about the future of our reality, I started co-organizing a conference in collaboration with Princeton and Johns Hopkins to try to understand what is the future of our reality going to look like? What's the role of deep fakes? What's the role of neurotechnology that might shape away our freedom or our agency? What's the role of AI as we become more and more dependent on it? And bring together scientists, engineers, science fiction authors, because they think outside the box. Come and bring them together to find solutions about what are the next questions that we need to tackle ahead of time before the end of times? I'm not that cynical. I'm actually quite optimistic, but it's important to have these conversations. And with that, thank you very much for your time. I hope the future of our reality is bright and hopeful. Thank you very much.